Welcome to the deep dive. Today we're exploring something pretty mind-bending, inspired by thinkers like Sir Roger Penrose. This idea, mathematical Platonism. It suggests math isn't just, a tool we use to describe the universe.
Right, not just descriptive.
Exactly. It might be the actual blueprint, the bedrock of reality itself.
And that's our mission today, really.
Yeah.
To dive into why certain, let's say, elegant, but also kind of strange number systems seem so fundamental.
Change is a good word for it.
Yeah. Why does physics, especially at the quantum level, seem to absolutely require things like complex numbers? And, what happens when we go even beyond those?
Okay, let's jump right in there. Quantum mechanics. You hear sometimes that complex numbers, with the square root of -1 are just a mathematical trick, a convenience.
Yeah, shorthand.
Yeah.
But that's really not the case.
No.
No, physics just, it falls apart without them. They are absolutely mandatory.
So why? What is it about them?
Well, it boils down to the central object in quantum theory, the wave function, usually written as psi-c. It's inherently, irreducibly complex. It has two parts baked in, if you think about its polar form.
Okay, so you've got the magnitude. That connects to probability, right? Finding the particle.
Exactly. That's the part we can eventually measure, sort of. But then there's the other piece, the phase.
The phase.
And that's the crucial bit.
That's the engine. It's an angle, this kind of circular degree of freedom, and it's entirely responsible for quantum interference.
Interference, like waves adding up or canceling out.
Precisely. Constructive, destructive interference, all that quintessential wave behavior. It comes from that complex phase. Without it, quantum mechanics just wouldn't have its wave-like nature. It's fundamental to reality.
Okay, but wait. If the phase is part of reality, but we can't directly measure it, how do we get from this unseeable complex thing to the real probabilities we actually observe in experiments?
Right. That's the magic, or rather the mathematics of the Born rule.
The Born rule.
Okay.
It's the rule for observation. It tells you exactly what mathematical step connects the wave function to a measurable outcome. You have to take the wave function, 60c, and multiply it by its complex conjugate.
The conjugate, that's where you flip the sign on the imaginary part.
Exactly. And that operation, it precisely cancels out or erases that unobservable phase.
Leaving just a real number.
A real non-negative number, which is what a probability has to be. So measurement itself in quantum mechanics is this process of going from complex amplitude to real probability.
Makes complex numbers totally non-negotiable then. Okay, so if math BBC is mandatory, can we keep going? More dimensions, other number systems.
We can, but the path gets very narrow very quickly. There's a fundamental theorem here, Hurwitz's theorem.
Hurwitz, right.
It basically proves there are only 4 special number systems defined over the real numbers that have the right kind of algebraic consistency. It's called norm division algebras.
And those are in...
Well, the ones we know. The
Yeah.
reals, the complex number.
Yeah.
That's interesting. Quaternions.
4 dimensions.
And finally, the octonions. 8 dimensions. And that's it. That's the list.
Only 4. Okay, but you lose things as you go up.
Yeah.
Right. Complex numbers, for instance, you can't really order them like you can real numbers. There's
Yeah.
no bigger than.
You lose order. Then you jump to quaternions, 4D, and you lose something even more basic. Commutativity.
Meaning the order you multiply matters? Like A times B isn't necessarily B times A.
Precisely. With quaternions, an N times dollar does not equal J times E guy. It's actually minus TI. That non-commutativity, it seems like a flaw.
But it's not.
It's crucial. That's exactly the property needed to describe rotations in 3D space perfectly. It avoids mathematical problems you get otherwise.
Or like gimbal lock.
Like gimbal lock. And even deeper, this quaternion and algebra structure. It's mathematically identical, the term is isomorphic, to a fundamental symmetry group in physics called SU dual.
SU dollars, that governs quantum spin and parts of the standard model.
The weak force, yes. So the universe is actually using this non-commutative math of 4D numbers to structure rotations and fundamental forces. It's not a bug, it's a feature.
Wow. Okay, so reals, complex, quaternions, what's the last one? Octonions, 8 dimensions, what do they lose?
You lose something even more fundamental. Associativity.
Associativity, that's like A times B times C might not equal A times B times C.
Exactly that. The way you group the multiplication changes the answer. It's Well, it's algebraically bizarre compared to everything else.
That sounds deeply weird. How can that be useful?
But again, the weirdness is the key. This non-associativity, it turns out, is the unique source, the generator, for something called the exceptional Lie groups.
Exceptional, meaning they don't fit the normal patterns.
Right. They're these standalone, incredibly complex symmetry structures that don't belong to the regular infinite families of symmetries. And the biggest, most complex one.
Is E8, the 248-dimensional one.
That's the one. $80 It emerges directly from Octonian algebra. The weirdest of the four number systems generates the largest known fundamental symmetry group.
Okay, hold on. How does that connect back to physics? To the universe?
Well, think about the most ambitious theories trying to unify everything, like string theory or M theory.
Right, they operate in higher dimensions, 10 or 11.
Exactly. And the mathematical consistency of those theories, why they only seem to work in those specific dimensions, it's tied directly back to these number systems. Specifically, the 8 dimensions of the octonions are intrinsically linked to why superstring theory needs 10 dimensions and M theory needs 11 to be mathematically sound.
So the octonions are somehow dictating the possible dimensions for space-time in these unified theories.
In a deep sense, yes. The algebraic structure of the octonions provides the necessary mathematical framework, the scaffolding, that allows these theories to hang together consistently only in those dimensions. If, like, the universe's choice of dimensions is constrained by the properties of these numbers.
So let's try to wrap this up for you listening. What we're seeing is, well, it's kind of staggering.
It really is. The structure of reality itself, from the complex nature of a quantum wave function to the rules of rotation, even maybe the dimensionality of space-time,
isn't arbitrary. It seems constrained, maybe even dictated, by the unique algebraic properties of just these four number systems: reals, complex, quaternions, and octonions.
It suggests the laws of physics might not just be rules we discovered, but maybe the inevitable mathematical consequences of the only algebraic structures allowed.
So here's the final thought to chew on. If the really strange math, like the non-associative ontonions, is needed to unlock the deepest symmetries physics knows about, like E108, could it be that what we call the laws of physics are simply the fallout, the necessary results of the universe being built on the only four number systems it could be built on? Something to think about.